So welcome back. This is the experimental part of waves on a string, and I want to wish you well and stay healthy out there. And you know, if you need any help with your lab work, be sure to get in contact with your instructors. We're going to be sending out a little email explaining how the final is going to proceed. So right now it's still a little bit on the drawing board, but I'm pretty close to having all the details figured out. So may the Lord be with you again. And behind me, you can see I have turned on the experiment. So right over here, this is called a vibration generator. And it's basically a computer, it's actually a speaker. And you can hear it right now. It's making a sound, a low frequency. It's about 28 hertz. And it oscillates up and down, up and down, up and down. On the other end, we have 150 grams, producing the tension in the string. And you can see we have 1.5 waves on here right now. So if you count the number of nodes, remember the first one over here is 0. We got 1, 2, 3 nodes, and that's the same as the number of antinodes, which makes the experiment a lot simpler in dealing with the number of antinodes. Okay, so what we're going to do is we're going to turn on the strobe and let you see this thing in the dark. So I need to turn the lights off over here. And this is pretty cool. So you can see right now, can you see it?
Can see it really good.
So basically it's like I'm jump roping. If I get the frequency just right, I can make it go backwards. That's because I'm flashing on the string a little bit longer than one period. So it's gone a little bit too far in one period, and because I went a little bit short. And then if I go too short, then it travels a little bit longer. So I could make it go in opposite directions. Now, I can actually speed up the strobe so you can actually see like 2. Or right now I got 4. So you can see 4, and it's holding nice and still there. All right, I'll speed up. Now you got 3. So we're actually going so fast, we're seeing 3 points on the wave. And I want to get 2. 2 looks pretty cool. There it is. Slow it down. See, and then it'll go back the other way. See that? Whoop, 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 whoop. All right. So you can see those waves are traveling up and down, and if you freeze them at the right frequency, you can actually see where they are in their oscillation up and down. Every point along the string is like a spring oscillating up and down. Now at the nodes, it's not oscillating at all because the waves going in the 2 directions are killing each other, and so you're always getting 0. All right, here we go even faster. You can see, I saw about 6 of them in there. All right, so I'm going to turn that off. And turn the light back on. How'd that look, Mr. Sylvester?
It looked really well once I turned the autofocus off.
All right, so capstone is really easy to set up here. So if you remember, we did the lab where we did circular motion, and you plugged a couple of wires. These are called banana plug leads right here. So we got 2 banana plugs going to the output, just like we did with the circular motion. And we just go to the power supply. Now when you did circular motion, you used direct current. This time we're using a sine wave. And with a sine wave, you can change the frequency just by typing it in. So right now I'm at 28.44 hertz, and I'm getting 3 antinodes. Getting 3 antinodes. Here, you want to put that blue thing there?
Oh, that might be a good idea.
All right. So we're bringing in some contrasting color here, so you can see the waves a little bit clearer. How's that?
Much better.
Much better. Okay. So anyway, if I change the frequency to let's say about 30, almost 39 hertz, I can get the next one. So we worked these out before we got started. Okay, so this is 39 hertz. It's a little bit off. It needs to be adjusted. And that's what you'd be doing in lab. And you can see, bam, I got it right there. It's looking pretty good. And you can hear it vibrating. You can change, you go all the way to 1/100th of a hertz and just keep changing it until you get it to look as good as you can get. Anyway, so you can hear, I just changed the frequency a little bit and you can hear it change as I do it. Anyway, that's four antinodes right there. I'll do one more for you. I'm going to go up to about 80 hertz. Let's go to my favorite sound, 60 hertz. That's what you hear when you have bad speakers and it's time to get yourself a new speaker. And that's what's coming out of your wall socket in your house. 60 hertz comes out of your wall socket and that's how it sounds. That's a little higher. It's gonna blow! So we're going to 77. How's that look? That's pretty close. Now it's oscillating so fast you don't get much of a amplitude. So it's tough to see, but you can see I've got 1, 2, 3, 4, 5, 6, 7 on there. So you remember you got to take like 9 measurements. Okay, that's even a little bit, let's see. That's a little bit better right there. 1, 2, 3, 4, 5, 6, 7, 8. So 8 antinodes, and I'm at 78 hertz, which is the frequency. So it's oscillating about 78 times every second. All right. So I'm going to stop that for 1 minute. And I'll put more weight on there. So the second part of the experiment is you're going to use this string right here, but add different amounts of tension into the string. So I got 150 on there right now. And so what I'm going to do, I'm going to take it off so it's down to just 50. Now this string is pretty heavy, so there's kind of a limit that you can go because the string itself wants to fall to the ground, and because it's so massive, it could actually like be greater than 50 grams, but it's not greater, as you can see. It's pretty good. But let's see what we can do with that. So we now have 50 grams of force. So you multiply gravity times 50 grams, and that would give you the force. And then we're going to see what kind of effect that we get when we do it. Now, it doesn't matter how many antinodes you get. All we want you to be able to determine is what the frequency is and then what the wavelength is. So if you get like 4 bumps on the string, then you know you have 2 waves. So you put a certain amount of weight on the weight pan. That creates a certain tension. And then you can adjust the frequency until you get so many bumps. And when you get that, then you take the frequency and then measure the wavelength with the meter stick. But you don't even have to do that because the length of the string never changes. So in the beginning of the experiment, all you basically have to do is just measure this distance right here of the string length. And then when you get standing waves, then you just divide it up. So if you had 2 antinodes, you'd have 1 whole wave on the string. And so then the wavelength would be whatever the length of the string is. And if you had 4 bumps, then that would be 2 waves. So L divided by 2 would be the value for the wavelength if you had 4 bumps on the string there. And then you multiply by the frequency, and that'll give you the speed. So what we want to look at is speed. How fast does the wave travel when we put so much weight on the string? So let's go ahead, and we'll fire that up. Now remember, we took off 2/3 of the weight. And we're going to lower the frequency until we get a standing wave. really close. Let me go to a slightly, oh, that was good. That is pretty good right there. All right, that's good. So right now I am seeing one wave, two waves, three waves. So the length of the string divided by 3 is the wavelength, and I have a frequency of 35.51 hertz. And so for 50 grams, don't forget the 5-gram weight pan. So for 55 grams of force, I am creating a certain amount of speed in the string that is producing 3 waves. And so it doesn't really matter how many you get, just so that you can make a good measurement. All right. So that's that. Let's put a lot of weight on there. So I'll put like 250 grams. Let's see if we can see it. Wow, look at that. We're almost there. I'm going to up the frequency just a little bit. That looks pretty good right there. Again, you can change the frequency all the way down to 1/100 of a hertz. So here, I'll just change a little bit of that, so you can see. All right, so it's going up in frequency right now. Actually, I'm at 1/100 of a hertz. Too much. Okay. So you can just shape it. You can work it until it's like perfect. And that looks really, really good. Now notice that's 1.5 waves. So L is now equal to 3/2 lambda. So you'd multiply L by 2/3, and that would be the wavelength. And then the frequency is like 36.7 1 hertz right here. And so that's how you do the second experiment. And for the second experiment, we're actually changing the string. So you have to do two different trials, because things go pretty fast. Once you get the hang of how to set this thing up and make the measurements, we're going to use this fishing line right here. And this fishing line has a 30-pound test to it. It takes 30 pounds to break it. But it has a very, very low mass. Now, there's one control that we need to measure that we will put into the lab data when you get it. We need to know how much the string weighs per unit length. It's called the mass density of the string. And the symbol for it, the book uses mu for that symbol. So mu is equal to the mass of the string over the length. So before you set up the experiment, you'd find out how much string you need for the experiment, and then put it on a very sensitive balance. We have that milligram balance. And then mass the string, measure its length, and then determine the mass density right here. And as you know, you can tell, that yellow string is much more massive than this string right here. And you can be thinking to yourself, what would more mass per unit length mean as far as moving the string? What if this was made out of steel chain, and you wanted to put a nice wave on a steel chain? Just think how difficult that would be. And again, it's because there's so much mass per unit length. Now the equation that we're investigating for the second experiment is equal to the tension in the string divided by the mass per unit length. And then also the other equation you need is that the speed is equal to frequency times wavelength. All right? So those are the two equations that you need for this experiment. So it makes it real easy. All you have to do is measure the wavelength, multiply by the frequency, and then you get the dependent variable. And then your independent variable is right here. Are you okay? And that is the last lab of the semester. Crazy way to end, but but we're going to get through this. So may the Lord be with you. May His peace be with you. May you stay healthy and keep your spirits up. We're getting through this. We are going to get through this. And, you know, you can go outside. Just don't get with the crowds. All right? And Mr. Sylvester, you want to say sayonara?
Sayonara.
All right, take it easy, you guys.